Hello everyone, welcome back to my YouTube channel. I am Suhas Payar, studying third year CSC in Sri Venkateshwara College of Engineering. Today we are going to discuss a research paper on theory of computation. Firstly, introduction to theory of computation. It is a fundamental branch of computer science that explores the fundamental limits and capabilities of computation. It delves into the formal models of computation such as Turing machines and finite automata and investigates the nature of computational problems and their complexity. Formal languages and automata. Formal languages are precisely defined sets of strings or sequence of symbols that follow specific rules and patterns. They form the foundation for understanding and expressive power of different computational models. Automata theory explores the computational devices that recognize the process formal languages such as finite state machines, push-down automata, and Turing machines. These models provide insights into the capabilities and limitations of computation. Hierarchy of formal languages. Formal languages can be classified into hierarchy from the simplest regular languages to the more complex context-free, context-sensitive, and recursively enumerable languages. Computability and complexity. The theory of computability investigates which problems can be solved by computational devices and which problems are inherently computable or undecidable. Complexity theory examines the inherent difficulty of computational problems, classifying them into complexity classes based on the resources required to solve them. The P versus NP problem is a fundamental open question in computer science which explores the relationship between problems that can be efficiently solved and those that can be efficiently verified. The research paper title is Time-Space Efficient Stimulations of Quantum Computations. This work presents efficient stimulation of quantum computations with intermediate measurements via classical randomized algorithms and bounded error quantum algorithms. The simulations reveal that the languages solvable by bounded error quantum algorithms in time t and space s can be solved by unbounded error recognized algorithms in time O t log t and space O s plus log t, or bounded error quantum algorithms with arbitrary universal gates in the time O t polylog t and space O s plus log t. Introduction. This paper establishes two efficient stimulations of quantum computations with time-space bounds. The first result, a randomized simulation, enables quantum computations with intermediate measurements to be simulated by classical randomized algorithms with unbounded error. This simulation incurs a logarithmic factor override in time and a constant factor override in space, submerging and improving prior simulations. The second result, a quantum simulation, provides an efficient method to compile quantum algorithms to use any fixed universal set of gates with only polylogarithmic time and constant space override, strengthening the solvative theorem for finite precision models. Models of quantum computation. To support these simulations, a refined quantum computation model is developed to measure time-space complexity accurately, overcoming issues in previous models. An application of these results yield non-trivial time-space lower bounds for quantum algorithms addressing satisfiability related problems, specifically for MATSAT and MADMATSAT, which are NP-related counting problems. The bounds reveal that MADMATSAT lack a bound error quantum algorithm with time complexity and space complexity for any omega greater than 0, marking a significant advance in quantum time-space lower bounds. This section introduces a refined quantum computation model that accurately reflects time-space complexity, providing the core model definition for readers focused on the main results. The model aims to accurately capture quantum algorithms' time-space complexity, incorporating features such as sublinear space bounds, random access, and intermediate measurements. It also considers classical control obviousness to computation history, syntax, transition, aptitude, complexity, and absolute halting, ensuring practical feasibility and relevance to both computer science and physics. Early models, early quantum models like those by Bernstein and Vazarny and Watrous are fully non-obvious and support sequential access but lack random access, making sublinear space bounds challenging to implement. These models impose complex conditions or unitary evolution which complicate practical use and are partly due to non-obvious computation paths that may not be physically realizable. Our model. Our model is a classically controlled quantum Turing machine that operates on classical and quantum work tapes with multiple heads supporting random access, intermediate measurements, and both unitary and measurement operations on qubits. It addresses limitations in previous models, allowing complex quantum operations with an efficient syntactic structure. Randomized simulation. This section provides a general randomized simulation result showing that languages solvable by quantum algorithms can also be solved by unbounded error randomized algorithms with specific time and space overrides. It compares the new results with previous simulations, emphasizing improvements in efficiency, practically concerning handling intermediate measurements and the computational complexity of acceptance probabilities. The text outlines a method to simulate quantum computations efficiently while maintaining space and time constraints. It suggests a technique that allows for parallel computation of two related p functions, enabling the reuse of guess bits during the simulation. The algorithm guarantees that the probability estimations for the algorithm's acceptance are accurate up to a small error margin, ensuring a robust simulation of quantum algorithms in bounded error. Next, quantum simulation. In this section, the author aims to prove theorem with a focus on establishing a universal set of quantum gates and their simulation. They define a universal set of unitary quantum gates and state which asserts that any quantum algorithm can be simulated with a slight overhead in time and space by using an arbitrary universal set that closed under adjoint operations. The proof hinges on theorem, which provides a space-efficient version of the Solvay-Kitaev theorem, demonstrating that for a given unitary operator and precision parameter, a sequence of gates from a finite set can be generated to approximate the operator within specified bounds while maintaining polynomial time and logarithmic space complexity. The text discusses optimizing the space used in an algorithm that approximates unitary matrices, focusing on how to avoid storing intermediate results by generating them on the fly. It highlights the importance of maintaining a polylogarithmic running time while managing space constraints, leading to the introduction of a mechanism to output gate sequences in a specified order. In the proof of claim, we establish the existence of a sequence for a base case. The proof employs the triangle inequality and a series of inequalities to show the properties and hold through recursive arguments, while property 3 is verified using specific conditions on matrices and their approximations. The space complexity and analysis confirms that the algorithm uses space with optimizations, reducing the number of recursive calls and maintaining the required accuracy. Time-space lower bound. This section discusses time-space lower bounds for quantum algorithms, addressing problems related to satisfiability, building on prior research. Satisfiability has significant theoretical importance, yet proving its complexity lower bounds remains challenging. The paper derives that first non-trivial time-space lower bounds for quantum algorithms solving MATHSAT and discusses the implications of theorem. It highlights the open question of achieving quantitative improvements for lower bounds and emphasizes the need for bounds on simpler problems like satisfiability itself. Future research directions involve exploring efficient methods to derive these lower bounds and understanding quantum computational models better. Conclusion and future directions. Continuous advancement. The theory of computation continues to evolve, driven by the advancement of new computational models, the exploration of complex problems, and the development of novel algorithms. Emerging paradigms. It acts such as quantum computing and neuromorphic computing pose new challenges and opportunities for the theory of computation, expanding its frontiers. Interdisciplinary connections. The theory of computation intersects with various fields, including mathematics, physics, biology, fostering cross-pollination of ideas and driving the evolution of computational thinking. Thank you for watching my video. If you like the video, then please do like, share and subscribe. Thank you.